Hi guys, it's Jenny. I want to do a 10-minute challenge and see if I can review the key reactions from CHEM261 that you need to have a good understanding going into CHEM262. The first reaction I would say is important is SN2. This is substitution, where we have a leaving group and you've got a nucleophile which is electron rich, and it attacks and the leaving group leaves, and we basically substitute a nucleophile where the leaving group was. Okay, and this is strongly driven to the right when you have a strong nucleophile. So this works best when you have a primary or methyl leaving group, so alkyl halide usually, and it's got to be a good leaving group or a weak base so that it doesn't go back the other way. The next synthetically useful reaction is the E2 reaction. That's where you have a leaving group and you've got some beta hydrogens. And you've got a strong base, usually like hydroxide or tert-butoxide, and it's usually anti-periplanar, meaning it's got to be, let's say if this is wedged, this is going to be dashed, so anti to each other. That allows for orbital alignment and a fast reaction. Strong bases are usually things like hydroxide, methoxide, ethoxide, and if you need a bulky base, tert-butoxide. And if you recall, these are going to give us the more stable Zaitsev alkenes, which are the internal alkenes, and this one will give us the Hoffman alkene, terminal alkene. Now here we don't have a choice, but if you had a molecule where we had maybe an extra methyl group here, this would be the Zaitsev, and then you'd have the Hoffman product be the minor product, which would be this one. Now if you want to reverse that and make this the major product instead of minor, then you should use tert-butoxide. And here you would use maybe just hydroxide. Something else that makes elimination go faster is heat. So you often see a heat symbol as well. Now what if we had a molecule like an alcohol where OH group was not a very good leaving group? And the reason why is if I did elimination, let's say I have a base grab here and then this left, that would not be great because hydroxide's a strong base. So it might come back and attack, you know, some kind of a solvent and go backwards. And because this is so strong, the reaction will be driven to the reactant side. So in order to make this a good leaving group, many of you may remember, instead of basic conditions, I use acidic conditions. So that's what's going to set us up for an E1 instead of an E2. E2 is done in basic, strongly basic conditions, whereas E1 is done under acidic, and the whole purpose of that is to make the hydroxyl a better leaving group. So in this situation, we're going to have acid in the form of maybe sulfuric acid or hydrochloric acid. It's going to make this into water, which is an excellent leaving group because it's a very weak base. And then we're going to have the elimination proceed by some kind of a base, usually water. And this does not have an anti-periplanar requirement. We do not see anti-addition exclusively. So you're going to get a major product of perhaps the trans and some of the cis as well. So that's what I call part 1 is our chapter 7 reactions, SN2, E2, and E1. These are the most useful synthetically. This is how you go from one kind of molecule to another. So learn those really well and understand under which conditions they thrive. So E2 works really well with strong base. It can work for tertiary, primary, secondary. It works for all of them. It works best for tertiary because you get the more stable alkenes at the end. And for E1, of course, we are making a carbocation here, so we want tertiary, secondary, and then hardly ever do we make primary and methyl. If you had primary or methyl hydroxyl group, like let's say it was on the end of a chain, like pentanol, 1-pentanol, this would not be the best way to do it because that's a primary alcohol. So there are other methods of getting this OH group off of here. If it's primary or methyl, there's other methods, and we will learn those this quarter. Then I would consider chapter 8 is all about electrophilic addition. So part 2 of this review is how do we add things to a double bond. So let's say I have this molecule and I want to add to it all kinds of different things. Now what these all have in common is that my pi bond is acting as my nucleophile. So I want to know what are all the different electrophiles that will react with this nucleophile. Okay, grab onto your seats. We're going to go sort of fast, but you can always pause it or replay it as needed. Our first reaction is HX. This is going to attack our hydrogen because the hydrogen is partial positive and the halogen is partially negative. So think about this pi bond as electron rich, negative goes to positive, and then we pull the electrons toward the halogen. Now when you do that, you want the positive charge to form here and the hydrogen will go here. So the hydrogen goes on the less substituted carbon, and then you have the carbocation that's more stable, which is the tertiary one. And so this is based on Markovnikov's rule that we're going to add the substituent, which is X, to the more substituted tertiary over the secondary. And this X, by the way, is usually chlorine or bromine, but sometimes you'll see iodine as well. Now the next reaction we learned was if we did this with peroxide and heat or light to initiate the reaction, we will see the opposite regio selectivity. We'll see that halogen over here and the hydrogen over here. So this is what we call AntiMarkovnikov, whereas what we saw before was Markovnikov. It's good to think about these terms because that will help you remember what the reagents do. So what we learned next was how to add water. Now water is not really a great electrophile, it's more of a weak nucleophile. So what I need is some acid to catalyze this reaction. Now you can just think of this as H plus or H3O+. It's usually from either HCl, HBr, or it's from H2SO4 in water. Okay, so it's in an aqueous environment, which turns it into hydronium ion. So when you have acid present with water, you're going to basically do the same reaction as up here. So this is going to be very similar to this reaction. We're going to attack an H, make the more stable carbocation, and show the Markovnikov addition. But we're using water, not X. So it goes like this. I bring water back in from the solution, plenty of water in solution. And now this is a strong acid though, right? So I got a deprotonate here. Bring in another water, grab an H, let go of that H, and I've got an OH group and an H here. Here's my new group, and this is on the more substituted carbon, so this is Markovnikov. Now notice both of these reactions go through a carbocation intermediate, so you just got to make a note to yourself to watch out for carbocation rearrangements. Alright, so notice that so far the type of molecules we've made are alkyl halides, and we've made alcohols. So the thing is, I want a different way of an alcohol where maybe I don't want to see carbocation rearrangements. To do that, I use a different reagent called mercuric acetate. It's in a solvent called THF, and it's in the presence of water or alcohol. I'll use water in this case. It's sort of similar to all the other reactions where I use the pi bond to attack. And in this case, the mercury is my partial positive and my acetate is partial negative because of the O. So I'm just going to do the same kind of thing as before, but instead of making our carbocation right here, I'm going to use these electrons here because mercury is pretty large. It can come back and help stabilize by avoiding a positive charge. So to do that, notice mercury is getting attacked and it's also attacking, and that makes a cyclic loop between the alkene and the mercury. So what you're going to get is the mercury will drop one of its acetates, but it's still holding on to one of them, holding on to this one. This one breaks off. You have acetate in solution floating around, but now that's competing with water, and water is more plentiful and going to come in and attack one of these carbons. Now if you remember, positive charge here spreads to here and here, so think of these as partially positive right here. Whichever one is more stable as a partial positive leads to a lower activation energy for the attack. So that would be this one. So even though there's more steric crowding, this is driven by electronic factors. Opens up this way, so I'm going to end up with my OH group here, which means this is going to be Markovnikov. Now bonus question for you guys, what is the orientation of these? Are they cis or trans to each other? Well, hopefully you guys know that if this ring bridged intermediate formed, let's say it formed on the top or it could have been on the bottom, then my water is going to come in from the other side. It's sort of like a backside attack like SN2. So that means that this will be dashed and this will be wedged, or the enantiomer, right, where it's reversed. So just keep that in mind when you have a bridged intermediate, you end up with anti-addition. And then after deprotonation, we're going to also lose this mercury group by doing a second step called NABH4. So this is going to lead to the alcohol. And before we use NABH4, I'm just going to bring in another water molecule and just deprotonate this. NABH4 will come in and replace this HGOAC group. I have two ways of getting a Markovnikov alcohol. The next question is, how do I get an anti-Markovnikov alcohol? So if I want the anti version, I'm going to use this reaction here. Now for the first step of the reaction, we learned how the methyl group is bulky, and so you want the part of the BH3 that's not as bulky. So we have the BH3 hovering over the double bond, and then we have the boron wanting to attack here, and then we've got this group here, the pi bond here, breaking and forming a bond here, and this bond is breaking, forming a bond here. And the way I sort of know this is, well, I sort of work backwards. I know this is anti-Markovnikov, so I know that the BH2 group gets added here, but I also can reason it out. I know this hydrogen is more electronegative, and this is more electropositive. This is electropositive. So I know that it's going to be positive here to negative here. That's going to form a syn addition where these two are on the same side, or I could have them both in the front. So it's an enantiomer is also possible, where these are wedged and this one's dashed. And then if you have step 2, I'm going to, and by the way, that's a pretty detailed one that I don't require students to know, but that is going to replace the BH2 with an OH group. And it's in the back, so I'm just going to keep it in the back, but you also have the enantiomer. So this one is syn addition, and it's anti-Markovnikov. It's good to know both the stereochemistry and the regiochemistry. Now we've got halogenation, which you can say this isn't really polar, but in any given moment it could be polar. So you could treat one of these as having some kind of induced dipole. So we can do the same thing as before. But remember, with the large polarizable atoms like mercury, you can come back and prevent a carbocation here by forming a bridged intermediate. So it's exactly the same reaction. So notice that the bromine was attacked but is attacking back, putting a positive charge. It's on the top face. You also have the enantiomer, and you also have bromide. The bromide is going to come in and attack which of these carbons? It's going to be the one that's more stable as a positive charge. So I'm going to have more positive charge character here because it's more stable as a positive. What does that do to my stereochemistry? My bromide is coming in from the bottom, so this methyl group got shifted or pushed to the front, and this bromine is still on the front from right here. So notice that this is considered anti-addition. It's Markovnikov in the sense that my addition is right here at the more substituted carbon. Considered Markovnikov, but it's an anti-addition in terms of these being trans to each other. Now this is what I expect if I have aprotic solvent. So aprotic solvent is just going to help stabilize all the charges but not get involved. If I had a protic solvent, okay, sorry, that's Fiddler on the Roof. Okay. So if I had a protic solvent, it would come in and attack here. So instead of making my dihalide, I would have eventually an alcohol. So it'll require an additional deprotonation step. But I'm going to get an alcohol group here and a bromine there, or chlorine, and this is what we call a halohydrin. It's a kind of mixed functional group. And it's the same reaction as this one, just with the protic solvent getting involved as my nucleophile. So this is still all considered Markovnikov. I see my group that's added second being at the most substituted carbon. So for each of these reactions we just covered, you need to know, is it Markovnikov or anti-Markovnikov addition? Is the stereochemistry going to be anti or syn? And I'd like you to be able to identify who is the nucleophile and the electrophile through subsequent steps as well. Nucleophile, electrophile. When you emphasize these things, you will start to develop intuition, where you can look at things and figure out what's going to happen. And that's what we all want to do. And finally, we get to part 3, which are redox reactions. So I think probably the easiest reaction ever is this one. And actually, I'm going to draw it this way because this is a hydrogenation. So this is reduction. Okay, so the way that this works is you have hydrogen absorbed onto a surface that is what we consider a catalyst. So it's H2 molecules on a platinum or palladium surface, or even nickel or some kind of metal. You'll see what it is. And these guys just add on the same side. So you'll end up with, either both wedged or both dashed. And I would normally say plus enantiomer, but notice this molecule is not chiral. So sometimes what we'll do is we'll make it chiral by showing a different molecule. Instead of H2, we could use an isotope of H one called H2, and H2 is called deuterium. So D2 could be used instead of H2. And it's all hydrogen, but the D2 is heavier, so I can actually track it because it has an extra neutron. And so I can see deuteria on these spots instead of hydrogen. So now it does make it chiral. So I could say plus an enantiomer. And this is chiral because D is different from H, is different from a methyl, is different from the ring. So I have 4 different groups on this carbon and 4 different groups on this carbon. So that's the only reduction we learned. So now let's go to oxidations. The first oxidation is how to get a cis dihydroxyl group, so OH groups on the same side. And to do that, I'm going to use the same concept as before, where I had a molecule. Let's say I have like something like this, osmium tetraoxide, and I'm going to form OHs on the same side because it's all attached here. It's all coming in from one side. Again, it could be both wedged or both dashed because you're going to get both. And so these come in on both sides and this falls off. It's not really the official mechanism, but it's just a way to think about it to help you remember the stereochemistry. These are cis dihydroxyl groups. So the reagent you need is OSO4, osmium tetraoxide, and then you need some kind of a workup step, NaHSO3, sodium hydrogen sulfite. And sometimes we get lazy and not write this, but if you can remember or nice for you to know what it's for. It's a workup step providing us with a weak acid to keep these protonated. An alternative to this is sometimes you'll see cold KMNO4, and the K is just the counter ion, it's just K+. So we really care about the MnO4. So again, you're going to have the OHs come in on the same side, so you get the same product. So you get the same products, and this is with cold KMNO4. The reason why cold is needed is because we don't want to cleave the double bond. So we keep cold KMNO4 in basic conditions, and then we do a water. And sometimes you see water here, or sometimes you just see it as one step. So both of these reactions are what we call dihydroxylations. Hydroxyl being the OH group. It's fairly important to know that this is cis or syn addition. So now suppose we want to make a transdiol, so not a cisdiol. Then probably the best way to do that is to make an epoxide using a peroxybenzoic acid like MCPBA. MCPBA, metachloroperoxybenzoic acid. You can just know it as the acronym, you don't have to know the structure of it yet. You will later though. So let's say that this inserts an oxygen right into the double bonds, so we get a similar kind of intermediate as we've seen before with the Br and the mercury. So it's basically very similar in that it makes that bridged intermediate across the pi bond, preventing a carbocation from forming. And then we get opening of this ring, so we have one O, and so to make 2 OH groups we need another source of O. So the second step is to use acid. And the way that this works is I have my oxygen grabbing my source of protons. That activates this ring and makes it so that these carbons become partial positive. And so that's going to draw my water to attack here, thus making it a Markovnikov addition, just like for the other reactions that also involved a cyclic bridged intermediate. So what's going to happen here is, let's keep my stereochemistry, assuming this is wedged and this is dashed. Then once that opens up, I'm going to have this be wedged opening up here. My water attacked from the opposite side of the ring, pushing my methyl group that was behind to the front. And now I just have to neutralize. Whenever I see something like this, I have to neutralize that. So I'm just going to bring in some more water. I know there's water because I'm saying I'm using H3O plus as a reagent, which is H plus in water. So in the end, what this gives me is one OH group here and the other OH group here. And then my methyl group is here, and this is added to the more substituted carbon. So this is considered Markovnikov, but it's considered anti-addition because of the relationship of the OHs to each other. So just to recap, if you want the OHs on the same side, you use OSO4 cold KMNO4. If you want the OHs on opposite sides, you need to use MCPBA followed by acid as a separate step. Step 1, step 2. And finally, our last reaction is what happens with really strongly oxidizing conditions. We have either ozone followed by dimethyl sulfide or zinc in water. And what this does is this is ozone. It's a strong oxidizing agent, and it will cleave through this double bond. And when it does that, we'll just open it up a little bit, and you keep the pi bond there, but it broke in half, and you put oxygens in there from the ozone. Now if you want to redraw this, which I recommend, it looks sort of nicer if you redraw it. It will look like this. 1, 2, 3, 4, 5, 6. 6 is an aldehyde here. This H comes from here. So under reducing conditions, we're going to get aldehydes where there's a break. Otherwise, if it's carbon there, these are ketones. And then I also showed you another reaction under more strongly oxidizing conditions, like hot KMnO4, or you see KMnO4 with the heat symbol, followed by dilute acid workup or water. You're going to see the same thing, but instead of an H right here, you're going to get that oxidized as well, and you're going to have an extra oxygen in here. And then that's going to become a carboxylic acid instead of an aldehyde, because this is strongly oxidizing, more so compared to this, which has a reducing conditions. And there you have it. I don't think I made the 10 minutes, but there you go. At least you have the whole review in less than 10 weeks of class.